Good day, this is Jim Pytel from Columbia Gorge Community College Renewable Energy Technology Program. This is RT 120 Hydraulics. Today we're going to have a discussion about a particular type of hydraulic pump called Vane Pump. If you have not watched the lecture entitled Hydraulic Pumps, Gear Pumps, please go ahead and do so at this time because we discuss some critical concepts about hydraulic pumps in general. And then we're actually going to make use of these concepts to discuss vane pump. Okay, what I've drawn here is the housing for an unbalanced vane pump. And before I draw anything else in this thing, let's talk about what I like to discuss, the 5 major steps for any pump. So first off is suction, second, trap it, 3, squeeze it, 4, open it, and 5, seal it. And repeat. That's what an unbalanced vane pump does. How it does it is this cam ring with an off-center rotor. Because if it was centered, here's a cam ring and it's centered in a rotor. This distance between here is constant, the same, all the way through. Whereas if it was unbalanced with an off-center rotor, look at this distance here versus this distance here versus this distance here. Okay, this is how we get this thing to operate on the 5 steps for a pump. Okay, let's say this rotor is rotating in this direction. And inside the rotor are these slots. And draw this a little bit better. Inside a rotor, a slot, and there's a little spring here. This is just a certain type that pushes outward on this thing called a vane, hence the name vane pump. Just think of it as basically a scraper, a little piece of metal. When I say piece of metal, it sounds cheap. They're very precisely milled to match the surface of the cam ring and not scrape it up. But those vanes are forced outwards to contact the cam ring. And as that distance gets smaller, they can be forced back into that same channel. Okay, so they want to go out, but if the cam ring is pushing up against it right there, they'll go in. And that's exactly how that suction occurs. So let's say it's rotating in this direction as we determined earlier. How is it forming a suction? Look at this space is increasing in volume as that vane extends itself and it rotates in this direction. Just like I said earlier, here's our initial space and we expand it. It's lower pressure, things move into it. So suction has happened. We're sucking fluid into this spot. And what's this next step? Trap it. We're trapping it between those 2 locations. And now what are we doing here? Squeezing it, because look at this. Here's that same spot. It's getting smaller. 4, we open it up. Pressurized fluid shoots out. And 5, we seal it right here. Okay, so there's no path from out to in. There's no way to do it. And that's exactly how an unbalanced vane pump works. This particular model that I just showed is a fixed displacement. Model, because without changing internal components, we can't vary the displacement. So for every revolution of that shaft, there's a certain value, 4 cubic centimeters, cubic inches, it could be cubic centimeters, cubic inches per revolution. It's a fixed displacement pump. That's an unbalanced vane pump. Again, what is this guy right there? That's where the shaft goes, into that off-center rotor. Okay, there's something called a balanced vane pump, very similar to our unbalanced vane pump, and I'm going to go ahead and draw that, or at least a primitive rendition of it. So here's our primitive rendition of a balanced vane pump. I know it looks like the evil eye that's looking at you, but what is a balanced vane pump? What's the difference between that and an unbalanced? Well, the rotor is centered now. And what's neat about a balanced vane pump, there's two ins and there's two outs. And how this works is, think of just from this side. If this is our low pressure fluid in, again, it's being sucked in. There is veins. So these veins are forced outwards this way. It's sucked into this spot because this is an increasing volume. It's trapped, and I know I didn't draw two veins, it's trapped, and then it's squeezed and forced out of here. What's happening on this side? Well, exactly the opposite. Here's our in right here. I'm going to draw two veins this time. It's increasing volume, so it's sucked in. It's trapped. It's squeezed with decreasing volume, and it comes out that side. So all you got to do, tie these two guys together. There's our out. Tie these two guys together. There's your in. The advantage of a balanced vane pump, it's easier in shaft bearings. Basically, there's pressure on both sides that are equal and they are counter to each other. So it's not like one side is loading up on those bearings. We've talked about fixed displacement, and let's talk about our first variable displacement pump. Okay, so I'm going to redraw that. Here's our unbalanced vane pump. Here's those veins rotating in this direction. So here's an in, there's an out. And as long as there's eccentricity, basically saying as long as it is the rotor is off center of that cam ring, again, the cam ring is the outside, and the rotor's the inside. As long as there's eccentricity, I mean being off center, there is flow because, again, it's increasing volume on this side, decreasing volume, and it's forced out this way. What would happen if this shaft was movable? Or, even better, what if the cam ring was movable? Left and right. Aha. Okay, so now think about this. In a case where this is totally concentric, where all these volumes are equal, the thing is rotating in that same direction, there is no flow. Basically, you've established that zero movement there. There's your zero displacement, no flow. Here's your max flow. So this range, 0 to max. Okay, that is how it's done. A variable vane pump, a variable displacement vane pump. Basically, that cam ring is movable, or the rotor within inside the cam ring is movable. Okay, so let's just do this again. Here is an intermediate flow. Here's a max flow. No flow. Pretty neat, huh? Okay, so this is our first variable displacement pump. A variable displacement pump can also be what's known as pressure compensated. So a pressure compensated means basically, remember our pump curve earlier that we were talking about for increasing pressure, flow rate will go down typically. This little arrow addition there means that this pump can figure that out through a means of some mechanical and pressure pilot lines. Basically, it senses pressure, and what its ideal is for a certain range, let's say 500 to 1500 psi. If you set it at 6 gallons per minute, it's going to stay that way. Okay? If it wasn't pressure compensated, you would expect it to do something like this. Okay? So that's a pretty neat feature to have on a variable displacement pump. Because again, it's pressure compensation. And don't worry if you're not getting all of this right now. We're going to pop these things apart in lab and show you exactly what these things are. Okay, how do we do that for our unbalanced vane pump? Think about basically you can just twist this cam ring, and it's basically doing the same thing that eccentric cam ring. You're twisting that eccentric cam ring, keeping that rotor in the center. You're basically getting a situation where ultimately you could have a no displacement and you could vary it between max and minimum displacement. So the last thing to say about a vane pump, typically these things are given to you. It's what's known as a cartridge assembly. Basically, you're not going to go in there and replace a single vane. What they do is basically you get a cartridge assembly with a rotor and vanes already installed in it. And you just swap that out. So no sense in doing, even including that cam ring there. So in case you've scored something in there, you replace the whole back end plate, vanes, slided rotor, cam ring, and front end plate all simultaneously. That's a cartridge assembly, cartridge. Okay, so vane pump, two types. Unbalanced vane, balanced vane. They can either be fixed displacement or variable displacement, depending on if you've got this ability to establish concentricity, no flow, eccentricity, max flow. All right, we're going to move on to the piston pump.